The next talk is Scale Awareness of Light Field Camera-Based Visual Odometry by Niclas Zeller, Franz, Quint, and Stilla from the Karlsruhe University, and Niclas will be giving the talk.
Thank you very much. Hello, everybody. Welcome to my talk about scale awareness of light field camera-based visual odometry. First, I want to give a short motivation why we actually wanted to do visual odometry with the light field camera. Basically, what we have is a single sensor device, which is in the size similar to a regular camera. And therefore, it is, for instance, much smaller than stereo cameras, for example. Now, the advantage of such a light field camera is that we actually get depth information out of a single image. Here on the right side, you can see the image which is recorded by such a light field camera, and therefore, at least in theory, we should be able to also retrieve the scale of our scene when we do tracking and mapping. Our work concentrated on a focused Plenoptic camera, so this is just what I want to mention in advance. So everything which I'm going to talk about now will be related to focused Plenoptic cameras. Now, if we look at how actually the image is formed in a Plenoptic camera, we have a main lens similar to a regular camera, and we create an image of our object space based on this main lens. But now we place our sensor not in the image plane, but we place it basically closer to our main lens, and we put a micro lens array in front of our sensor. Now, this micro lens array creates focused micro images on our sensor, while neighboring micro images see the same scene from slightly different perspectives. Here again, a similar drawing. The problem what we have if we want to do multiple view stereo is that basically we always have to consider the diffraction of our main lens. So the traditional way to look at this camera basically is that we have our micro lens array and we have our sensor, and we are observing actually our virtual image, which is created by a main lens, but not really our object space. Now, our idea was to just project the micro lenses outside of the image space, project it into object space, as it can be seen here. We can do that for one micro lens, but we also can do that for all micro lenses. And basically, what we end up is a virtual camera array, which is now in object space and not in our image space anymore. And actually, we can use this camera array to do we can use this model and do basically standard stereo, standard multi-view stereo based on this model. And this is what our algorithm completely relies on. So if you look at our algorithm, we have a tracking framework, we have a depth estimation framework, and we have another scale optimization framework. I want to start to talk about the depth estimation. The depth estimation part. Here what we do, we calculate a semi-dense depth map directly on our micro image. This we do by finding stereo correspondences in the neighboring micro images. Here, semi-dense means that we only calculate depth for pixels which have sufficient intensity gradients, since those are only the pixels which carry information. And what we also do, we carry out a probabilistic depth map, so we calculate probabilistic depth hypothesis by establishing multiple stereo observations and then merge them in such a probabilistic way. Initially, we developed this algorithm for only single images, but with our new geometry, we can extend that to basically to a multiple view geometry to use also multiple images to retrieve depth out of it, and therefore really benefit from the larger stereo baselines. And what we end up with is a depth map which looks more or less like this. We have depth information for each of the pixels in our micro images. Now the problem here is that we don't have a one-to-one correspondence between our object space and our image space, since one object point is projected to multiple micro images. So what we can do, we can use this depth information and project it into our virtual image space, and so get a depth map in our virtual image space, which is a globally consistent depth map, and we have a one-to-one correspondence between object space and image space. And since we here also have larger neighborhood than in our micro lenses or in our micro images, filtering and outlier removal becomes much more easy in this virtual image. And of course, for all pixels for which we have depth information, we also can calculate intensities. So we get our keyframe representation, which is, we have raw image, a raw image depth map, a virtual image depth map, as well as a virtual image. But in the virtual image, we only have information at those pixels where we have gradient, where we have an intensity gradient. Now the next part would be the tracking. How do we do tracking actually? What we do is a method which is known as direct image alignment, how it was done already in LSD-SLAM, for instance, or also in earlier works which were working on RGBD cameras. What we do, we use a tracking reference, which is the virtual image of our keyframe. We calculate a point cloud out of that. We project it back into the micro images of a new recorded frame, and then we optimize our relative pose between the keyframe and our new recorded frame with respect to the intensity error in this projection. We do this in a coarse to fine approach to increase basically our region of convergence, and we also constrain our optimization by a linear motion model. So basically we predict based on the linear motion the relative pose of our new recorded frame, and we use that to constrain our optimization. And here on the bottom you can see how in the different iterations how actually our residuals are decreasing and how we end up with a very low residual at our optimum solution. Now the final framework which you have is the scale optimization, since in every, as it is in monocular visual odometry algorithms, we also will face drifts, especially scale drifts in our Plenoptic camera-based approach, in our light field camera-based approach. So we further use a scale optimization framework to account for those scale drifts. And scale optimization basically is done in a way similar as tracking is done. What we basically do, we use a keyframe which is finalized. So if we select a new keyframe, we use the last one and basically do something like tracking it on its own. So we calculate the point cloud out of the depth map and project it back to the micro images of this keyframe, and then we optimize the intensity error with respect to the scale of this depth map. And so we get for each keyframe we get a scale estimate, and furthermore we do filter over multiple scale estimates. Therefore we use just a regular linear finite impulse response filter to filter over multiple scale estimates, and in that way we get a more or less stable scale estimate for each of our keyframes, which we can use to correct our keyframe poses. Here we consider the correlation between neighboring keyframes to be quite high, and so we have this correlation factor C, which basically models the correlation between the keyframes. So if the distance between the keyframes is high, we have less correlation, and so the scale can be more different between those keyframes. Now we also wanted to evaluate our algorithm, and the problem basically was there are no data sets available which are similar, which can be used to evaluate our algorithm, and on the other side there are no other comparable algorithms available which we could use to compare our algorithm to. So what we decided to do is use this platform, which you can see here on the right, and record actually synchronized sequences for the Plenoptic camera as well as the stereo camera system. And in that way we were able to compare our algorithm to existing stereo approaches as well as monocular approaches. And here we basically compared it to state-of-the-art approaches for stereo cameras as well as monocular cameras. Now what we do, since it's hard to measure ground truth for large-scale trajectories, we decided to record all our trajectories in large loops, where beginning and end of the sequence actually result in the same point, and in that way we can measure the drift from beginning to end of our sequence, and in that way get a metric for the accuracy of our algorithm. yeah, now here I have a short video to show this, how this algorithm looks like if it is running. On the left side, we see our recorded raw image from the Plenoptic camera. We see the depth map of each keyframe, and we see the corresponding intensity image for the keyframes. And on the right side, of course, you can see the estimated trajectory as well as the generated semi-dense point cloud. Yeah, this is an indoor scene, but we also recorded some outdoor scenes. So there are really diverse scenes, I would say. And if you see, the drift from beginning to end is actually quite small. Now, to show this in numbers, I draw some so-called cumulative error plots for all of here for the absolute scale error. Of course, here we can't compare them to the monocular approaches since they are not able to retrieve the absolute scale. But if we compare now to a stereo algorithm, of course, the stereo algorithm performs much better than our Plenoptic camera-based approach. But still, it has also a much higher stereo baseline, and still we are able to retrieve somehow the scale of our scene. For more than half of our scenes, we were able to retrieve the scale with an accuracy better than around 10%. Now, what's actually nice to see or interesting to see, if we look at the scale drift and we compare our algorithm to monocular algorithm compared to direct sparse odometry, for instance, which is really state-of-the-art in monocular visual odometry, we see that our scale drifts are much better than those of DSO, and even far better than those of OrbSlam, basically. Then finally, looking at the alignment error, which is more or less an absolute metric over the complete trajectory. Here we see that we perform slightly worse than DSO, but this can be explained quite well. Since DSO is doing an optimization in a window over multiple keyframes, over up to 7 keyframes, we only do pose estimation based on a single keyframe. So if we would use a light field camera with such an window-based optimization, I think we could further boost the accuracy of our Plenoptic camera-based algorithm. Yeah, now before I close the presentation, I want to do some advertisement for my PhD supervisor. So if you enjoyed here in Munich this year, maybe you want to come back next year again, because there's PI 19 at Technical University of Munich. Thank you.
If you have questions, please step forward to the mics. I'll start with a quick question. I'm trying to understand the depth estimation. So you said you have a single image method that then you augment with, basically, because you have multiple views.
Yes.
Is that jointly done, or it's you first do the single image depth estimation?
I first do the single image depth estimation for each keyframe which I select. I do a single image depth estimation, and then I track new frames. And as I track new frames, I get new information, and I use this information to get new depth observations, and those are then fused in this probabilistic model, basically.
Is there a way to potentially do that jointly? I mean, because instead of doing it in single image.
Yeah, I can't do it jointly because the images come time after time, so they come temporal. So if I have a frame, then I directly use it for doing the depth estimation. Right. Okay. But yeah, what you could do, you could do a joint optimization as it is done in DSO, for instance, and then you would probably get even better results.
Okay, right. Thank you. If there are no more questions, let's thank